Bragg's law. So again, Kim Libre, it's a really short section here. So here it's kind of explaining the different lattices and the law. There's not much to it. So mathematically, we have n because we can have these multiple orders, and that's what's nice about this one, showing that if we have a crystal lattice, we have these repeating planes, right? That's the whole point of it. And so if you have a wave coming in and it scatters off these different ones, we have that difference. So we can have diffraction between A and B, diffraction between C and B, but we can have a higher order one between A and C, and we have that repeating lattice. That's what N represents. So we usually start at 1, 2, and the probability falls off. The intensity 1 is the strongest, and so on. But that's not the most important thing. The most important thing is that it relates that wavelength, the angle, and the lattice spacing. So the wavelength of the light coming in, the angle, and so here we can see the instant angle in this. So usually in data, we usually talk about 2 theta because that line comes down. You have 1 theta coming back to the origin, and then another theta coming up. And so relating that angle with the lattice spacing d. All right, so switching over to Wikipedia again, a nice little graphic showing that we usually show these waves coming in, and we talk about constructive and destructive interference here. And um, but it's a wave of potential. So that's what's happening, is that scattering in all different directions. And we're most concerned when those waves, they overlap to give us this constructive interference. The other extreme is destructive interference. But the constructive gives us the bright spots that we use to indicate it. And so that's what we're concerned with. There's again some same type of thing and so on. And then down here, we can see a diffraction pattern and we can see those bright spots, right? That's really where we have the most constructive interference, and that's what it's good for. As far as the math of solving it, the only thing to go back to is here. So sine theta has no units. So it's really mashing up the units of the wavelength, which is usually in nanometers or angstroms, to the lattice spacings. That's again, usually nanometers is what we talk about. So just matching those units is the only important thing. Okay, you have the simple calculations you can practice and get those numbers down, but not much to this one, for just have to know the equation.